In this chapter, we're going to investigate two classic problems that effectively kickstart the entire study of calculus. One of them is called the tangent line problem, and the other is called the area problem. Now, both of those problems, though, are based on the notion of limit, and that is the idea that we want to investigate in this section. Consider this function. Now, notice that the function is described by a fraction, and we know that fractions have the characteristic that their denominators cannot take on the value 0, because that makes the fraction undefined. And that means that x cannot take on a value that will cause this denominator to be 0, and in this case, then, x cannot take on the value 2. So we can't evaluate f of 2. F of 2 is undefined for the function. But we can investigate for the limit of the function as x approaches 2. That is, what value does the function approach as x approaches this target value 2? Now, the notation associated with the idea is this. It's the limit as x approaches 2 of our function is equal to what number? Now, to find limit or to make this discovery, we can use either a table of values or a graph for the time being, and each of those will give us a pretty good idea of what this limit notion is all about. For a table of values now, we have this target point 2, and we let x take on values that are a little bit smaller than 2 and a little bit larger than 2, and we're investigating for the value of the function as x approaches 2 from either side. All right, here's how it goes. Now, notice that x is taking on values that are a little bit smaller than 2 here at 1.9, and then 1.95, that's a little closer to 2, and 1.98, that's a little closer yet to 2. And on the other side, we go all the way over here to 2.1, and we approach from the right side. So we have 2.1 and 2.05, 2.02. So the approach from both sides. All right, let's see what happens. F of x, you see f of 1.9 is this value, f of 1.95 this value, f of 1.98 this value. Now notice the trend here, 2.95, 2.975, 2.99. So as x approaches 2 from the left, f of x is approaching what value? Now we know that f of 2 is undefined. You see, but all we're investigating for is what value is f of x approaching, you see, as x approaches 2. That's the idea. It looks like it's approaching 3 here to me. Let's investigate from the other side. F of 2.1 is this value, f of 2.05 this value, f of 2.02 is this value, 3.05, 3.025, 3.01. It looks like as x approaches 2 from the right that f of x is approaching 3. And it does turn out that for this problem, the limit as x approaches 2 of this function does turn out to be 3. Another way to investigate the idea is like this, using a graph. Now, we're thinking as x approaches 2 from both sides, that is, as the value of x approaches 2 from the left, what does f of x approach? You see, where are we going with our graph? What is it getting near? Well, let's see, this is 1, 2, 3, and notice a little hole in the graph because our function is not defined at f of 2, so we put a little hole in the graph. But clearly, f of x is approaching 3 as x approaches 2. So we look at the approach here to our target point, and what are we approaching here with our function value? And then we investigate from the other side. As we get closer to 2 from the right side, it looks like the f of x also is approaching 3. So no wonder we have a situation where the limit as x approaches 2 of our function turns out to be 3. Now, I've written another limit up here, and let's investigate this situation graphically. The limit as x approaches 0. Well, let's look back over here. As x approaches 0, you see, from the left, what is f of x approaching? Looks like it's approaching this value right here. You see, as we get close from this side, f of x is approaching 2. As we get close from this side, that is, as x approaches our target point 0 from the right, our f of x is approaching 2. Now, couldn't we just evaluate this, though? I mean, after all, if x takes on the value 0, you see, our function is defined at 0. Would we not get this value 2? Well, let's see. If x is 0 and 0 and 0, we would have negative 4 in the denominator. Negative 8 divided by negative 4 would indeed be 2. So it does turn out that if our function is defined at our target value, and if our function is continuous in the neighborhood around this target value, then f of the target value becomes the limit. But we're going to investigate some much more interesting situations than the situation where the function is defined at the point. All right. Now, it is also the case that even if the function is defined at the point, if the function is not continuous at that point, then we have some interesting things going on with limit. Consider the same function we had before. Basically, we have f of x described in a couple of ways. So we have a piecewise function here. But this is the function that we had over here. So f of x follows this pattern, or is this value when x is not equal to 2, but f of x is 5 when x is equal to 2. All right, so the graph of that looks like this. It's the same graph that we had before, except the function is defined at the target point too, because f of 2 does turn out to be 5, you see. So we do have a graph point for that value. You see, it's often thought that if f of the target point exists, if we can find it, then that is the limit. But that's not always the case, because we're really looking for the value that the function is approaching, not the point, not the value that it becomes when it arrives at the point. It's what it's approaching. So here, once again, it's the idea that as x approaches 2 from the left and from the right, f of x is approaching 3. So the limit here turns out to be 3 and not 5. All right, here's another situation. We have a situation here where the function is not continuous at our target point, which once again is 2. Now we investigate the limit as x approaches the target from the left and from the right. Now, from the left, if we're thinking about the limit as x approaches 2 from the left. Now notice f of all of these values, it looks like a constant function in this interval, you see, and certainly it is, that f of negative 1 is 3, and f of 0 is 3, and f of 1 is 3. And the point 3 is on the graph. That is, f of 2 is 3. You see, and once again, it's thought that if f of the target point exists, then that's the limit. You see, and f of 2 turns out to be 3, and therefore is 3 the limit. Turns out that it's not, because when we investigate from the left, we find the limit as x approaches 2 from the left. Notice the notation. Approaching 2 from the left, f of x turns out to be, that is, the limit of f of x turns out to be 3. But the limit as x approaches 2 from the right of the function turns out to be, well, let's see, as we approach from the right, for all of these values, f of x turns out to be 1, 2, 3, 4, 5, 6. So what are we approaching? We are approaching 6, you see, from the right. Now once we arrive at 2, it's a different value, but we are approaching 6. Now in this circumstance, when the limit from the left is not the same as the limit from the right, we say that the limit generally of our function does not exist. Here's another example of a limit which doesn't exist. We're dealing with a graph here, and our target point is 3, so we want the limit as x approaches 3 of this f of x. Now here's what we know about the situation. When we have a dotted line like this and the graph is approaching that dotted line in this manner, we know that this is an asymptote. So as x approaches 3 from the left, f of x is approaching infinity. That is, it goes up without bound here as we get really close to that vertical asymptote. In a similar way, the graph is rising without bound as x approaches the target point 3 from the right. So as x gets close to 3 here, f of x is going up without bound. Now in this circumstance, we say that the limit of the function at that target value doesn't exist, because we don't have a real number that this function is approaching. And that's kind of a key idea here. Although the limit is sort of the same in concept, that we're approaching infinity from both sides, that we don't use infinity as the limit of a function. Okay. Here are the situations in which limits do not exist. And there are 3 of them, and we've looked at 2 of them. We've looked at the first 2 here. F of x approaches different values from left and right, and under that circumstance, the limit of the function at that target point does not exist. And in this one, we found that we have a non-existent limit when f of x approaches plus or minus infinity as x approaches the target value. Now, a third situation is rather intriguing, and we're going to look at this one on the graphing calculator. F of x oscillates between 2 fixed values as x approaches the target. Rather intriguing graph emerges, and here's the example we're going to look at. It's the limit as x approaches 0 of the sine of 1 over x. The sine of 1 over x. Take a look at a table of values, and we'll understand what we might expect here. As x takes on values that approach 0 from the right. Now notice I'm using 1/10 here, 1/100th, and 1,000th. So I'm getting really close to 0 from the right. But it's not x that we're taking the sine of. We're taking the sine of 1 over x. 1 over x turns out to be, well, let's see, the reciprocal of 1/10 is 10. The reciprocal of 1/100th is 100. The reciprocal of 1/1000th is 1,000. Now look at what's happening to the graph within these little intervals. We're taking the sine of the values that are between 10 and 100. Between 10 and 100, gee, that's 90 units in here, over which we have this sine curve. And the sine curve, one complete cycle, occurs in every 2 pi length, as you recall. So how many cycles of the sine curve would we have here? Well, in this little bitty interval here from 0.1 to 0.01, which gives us these that we're taking the sine of and all the values in between, we actually have 14 cycles of the sine curve right in there. Okay, now consider what happens between 0.01 and 0.001, or between 100 and 1,000. You see, now this interval that we're thinking of taking the sine of those values, you see, turns out to be 900. Gee, how many cycles do we have there? Well, it turns out that we have 140 cycles of the sine curve in that interval. Wow. That means the closer we get to 0, the more of this business we have going on. You see, and you know the sine curve goes from 1 down to -1, so we're just kind of bouncing from 1 to -1, and we're kind of bouncing faster and faster as we get close to the target value 0. Let's take a look at it on the graphing calculator. Here's our function, and I've made window settings of x minimum -5, x max of 5, and the y minimum and maximum are at the bottom and top of the amplitude. The graph looks like this. You see, there's just a little disturbance here in the middle of the graph. The graph looks kind of normal out here and over here, but right in here there's kind of a disturbance. Let's concentrate on that disturbance area by coming into, oh, let's say -1 and 1. Seems to be more disturbance. Let's come in a little more. How about -0.1 and 0.1? Well, it's even more disturbing the closer we get, it looks like. And as a matter of fact, the calculator isn't even able to show us a clear picture of all of the cycles that will occur as we concentrate on or magnify the interval right in this region of the coordinate plane. There are just too many cycles for the number of pixels on the calculator to be able to display what's really going on. So no wonder we have a limit that just doesn't exist. Sometimes finding the limit is a rather predictable situation. We've already talked about the notion that if a function is continuous in a neighborhood around the target value, then f of the target value is the limit. That's the way it can be calculated. And some circumstances are rather obvious. For example, if we want the limit as x approaches 2 of 7. Now this is just a constant function, y equals 7. You know, it's just constantly 7. So clearly as x approaches 2, you see, for every value of x, the function becomes 7. F of any x value is going to be 7. So the limit as x approaches 2 would of course be 7. Now this is generally the idea that the limit of a constant, you see, the limit as x approaches some value of a constant will be that constant. Here's another one that's fairly trivial. The limit as x approaches 2 of x. Well, the function here is y equals x, a continuous function, you see. And it's the notion that f of the target point is going to give us the value that we're looking for the limit. So f of 2 means replace x with 2, and what do we have? We have 2. In a similar way for this one, the limit as x approaches 2 of x cubed. You see, once again, we have a continuous function. And by the way, I'm using this word continuous, and you understand that continuous means that we don't have breaks in the graph, fundamentally. Or that we don't have holes in the graph or anything like that. You can draw the entire graph by leaving your pencil on your graph paper. That's the notion of continuity. And there's actually a lot of discussion about continuity when you get into the calculus area. For right now, we're dealing with simple enough functions to where we understand when we have a continuous function and when we don't. It's pretty obvious from the type of function that we have because we've studied them in the past. All right, anyway, we have a continuous function here for x cubed, and so f of the target value will be its limit. And 2 cubed then is 8 for the limit of this function. All right, what about this one? Well, gee, we have some restrictions here. We have the 4th root of x. Now, we know that x has some restrictions. We can only take the 4th root of positive numbers, so x is greater than or equal to 0. But our limit is the limit as x approaches 2. That's a positive number, and this graph is certainly continuous. If we recall the nature of the graphs of this kind of our radical functions, we know that all we need to do then is take f of this target point 2. So f of 2 would mean the 4th root of 2, which is our limit. Here's another one. Now, we're just introducing more and more restrictions on the function, but we're thinking about, or we should kind of think about the target point. What's happening in the neighborhood of the target point? Do we have any restrictions there? That's the idea. Now, in thinking about this, consider the notion of 8. Well, we know that in the denominator, x cannot take on the value 4 because it would cause the fraction to be undefined. All right, so that's a problem area. But 4, x equals 4, is not in the neighborhood of our target right here. So we don't really have to worry about it too much. Now for the numerator, in the numerator we know that we can take the square root of positive numbers or 0. So x has to take on values that will cause this radicand to be positive or 0, and at our target point certainly we have that condition. Now because of that, we're not in any restricted area here with our target value, so we can simply take f of the target value. And you can look at the graph of this if you want to on the graphing calculator to verify continuity. But in the neighborhood of the target value, we do have a continuous function. So f of the target number turns out to be the limit. Now let's evaluate that. If x is 8, we have 8 plus 1, 9. The square root of 9 is 3. So we have 3 in the numerator. And let's see, 8 minus 4 is 4 in the denominator. So the limit as x approaches 8 of this function turns out to be 3/4. Here's another situation. We have a piecewise function once again. F of x follows this pattern when x is less than 2. F of x follows this pattern as when x is greater than 2. Now it looks like 2 is a real neat target point, and it turns out that we're trying to evaluate the limit as x approaches 2 of this particular function. Well, all we want to verify is that the limit from the right and the limit from the left are exactly the same value. We can almost do it by observation here. We're going to do it graphically too, but by observation, think about what happens as we get very near 2 here, as we approach from the left. Now what happens if we're at 2? Now I can evaluate this expression at 2 if we want to. You see this expression is the expression for a continuous graph. Now we're only defining it for a portion of our coordinate plane. We are limiting the domain of this, you see, but I can certainly think about f of a 2 appropriate for this. If x is 2, 2 squared is 4, 4 minus 4 is 0. So if I was allowing 2, this expression would become 0 when x is 2. All right, and in a similar way, this expression would become 0 if x is 2. You see, now it can't be 2 because of these restrictions, but the idea is that they are both approaching 0, that is, f of x is approaching 0 for both of these circumstances when x approaches 2 from the left and from the right. All right, so it turns out that the limit as x approaches 2 of the function turns out to be 0. We can maybe see it a little more clearly if we look at the graph. Now the graph, let's see, when x is less than 2, the graph would look like this. This is x squared minus 4. So it's a parabolic curve along this interval, you see, of our domain. And out here, defined at x values greater than 2, we have a linear function. And at x equals 2, the function is not defined. But in both circumstances, we are approaching 0. That is, the function is approaching 0 when x is approaching 2. So, I think to broaden the idea just a little bit, it doesn't make any difference about the definition of the function at the target value. You see, we could have defined f of 2 to be 0. We could have defined f of 2 to be 5. We could define it, leave it as an undefined value as it is here. That doesn't make any difference. It is the value that the function is approaching when the target point is approached. See, when x is approaching 2, what is the function approaching? That's the idea of limit.